Hi there, welcome to this first installment of Let's Design a Drug. The whole goal of this project is to show you how in-silico computer modeling can actually be used to design real compounds that actually bind to the target that we intend them to bind to. For this project, I'm going to be choosing the cannabinoid type 2 receptor. I wanted to shy away from possible molecular targets that could lead to drugs of abuse. For example, I didn't want to do anything with the opioid receptor, as these compounds can unfortunately be pretty addictive. And I also kind of wanted to shy away from NMDA receptor, mainly because of I don't really want to make a compound like ketamine, to be honest. And then, of course, with cannabinoid type 1 receptor, I don't want to make a spice compound. So, we're going to choose cannabinoid type 2 receptor, which has a lot of utility in possibly making therapeutic drugs for even things like autoimmune diseases and these types of disorders. So, let's get to it. So, whenever I'm thinking about a project such like this, I first think about where am I going to get the receptor that we want to dock our drugs or ligands to. And that source is going to be the protein data bank. So if we just go to Google, just a search bar, go to protein data bank, hit search. This is the RCSB PDB. This is the server that we're going to use. So the protein data bank is a large host where different biological structures are uploaded that are from peer-reviewed publications. And you can pretty much search anything. You can see down here there are coronavirus resources. You can actually get the SARS-CoV-2 spike protein from this web service. But we're actually going to be typing up here the protein that we want, which is cannabinoid type 2 receptor, or also abbreviated as CB2. Cannabinoid type 1 receptor would be CB1. Serotonin 2A would be 5-HT2A. So they're also abbreviations. You can type an abbreviation or a long form factor of the protein. I prefer the abbreviations, they're faster to type. So CB2, enter. So here are all the entries we get. These codes up here are called PDB IDs. These are unique identifier codes to identify what that protein is, much like an IMEI number for a cell phone or a serial number for a product. Same idea, random sequence of letters and sometimes numbers to identify something specific. I want to develop a cannabinoid type 2 receptor agonist, not an antagonist. So the watered down version being a drug that turns on the receptor versus a drug that turns off the receptor being an antagonist. So sometimes in the structure description, it'll say whether or not the structure is an agonist or an antagonist. If it does not say, you can click this link. That was random. It said the link was unsafe, but I know this is a fine link to use. That was random. But anyway, so we click that link. This takes us to the DOI, which we can get the publication from. Lots of crystal structure papers are published in pretty prestigious journals, as these are hard things to do, get crystal structures for receptors. These are quite complex. This takes a team of scientists to do. What it tells us is that the crystal structure that we're looking at is an antagonist bound with AM 10257. So that is not a crystal structure that we would want to use. So if it doesn't say in the description, you can search, you can go to the publication and see if it's agonist or antagonist bound. So we can go back. We would not want to use 5ZTY or 5ZTY if you're American. Okay, 6KPC is a CB2 receptor, as it says right down here, and it's an agonist-bound crystal structure, so we could use this one. That's an option for us. 6PT0 says this is let's see, this is a CB2 receptor, says right here, and it says it is an agonist bound with Win 55212-2. It also has the G protein attached, which doesn't really matter for the kind of molecular modeling we're doing. It doesn't matter if we have the G protein or not. We'll get more into that. So we could use that structure. 6KPF. 6KPF is I believe this is I looked this one up. It doesn't say whether it's agonist or antagonist, but it's an agonist bound cannabinoid type 2 receptor. Doesn't say, but you could look it up. It says right here, cannabinoid type 2. 6KPG, this is a CB1 receptor, says right here. Make sure you look at the macromolecule before you just decide to use a structure. So we have those three options of crystal structures we could use. The other option, which some of you suggested that I don't want to go down this route, is AlphaFold. Some of you may have heard of AlphaFold. AlphaFold is the artificial intelligence server that predicts protein structure based on amino acid sequences. It's pretty good. I've looked at some of the structures. The problem with a lot of these things is even if they're off by like a tiny amount, 1 angstrom, it can honestly screw up your results. It's not the best thing to use a structure that is not determined by X-ray crystallography. I think it'd be cool to try a project where we do something with AlphaFold, but for this project, we're not going to use AlphaFold. If you are curious about AlphaFold, we can just go to it. AlphaFold. That takes you to this website here, and you could type in your receptor cannabinoid type, or cannabinoid receptor 2. And with AlphaFold, it has the receptors in different species. In this case, it's CB2 receptor in a mouse, rat, human, which is what we would want. The basic idea is that receptors in different species and animals do have slightly different amino acid sequences. Most of them are actually the same, but the human CB2 receptor is different from a rat CB2 receptor, which is different from a mouse CB2 receptor, although overall the sequence homology is quite similar. But we would use human receptor. And if we wanted to download, I do want to show you, if we wanted to actually download this receptor and use it, you would click it. You would click PDB file, and that will download the file right down here for us. But we're not going to be using AlphaFold structures. You can mess around with this if you want. It's pretty cool to look at. I've looked at a lot of the AlphaFold structures. Let's get into how to actually view these structures. There are lots of options for modeling software that you can use to view proteins in 3 dimensions. The one I use is Maestro. Maestro is a product of Schrodinger. This is quite an expensive program. An academic license is not so bad, but an industrial license is quite a bit of money. There's a free version of Maestro, which I highly recommend every one of you download and kind of follow along. The free version allows you to view protein structures, and it's probably in my opinion, the best software for just viewing 3-dimensional structures that come from the PDB. There's other stuff. There's AutoDocVino, which is free. I'm not as big of a fan as these interfaces. I like Maestro better. So I'm going to open Maestro. Wait till that opens. Okay, that opened. We'll drag that to my screen so you guys can see. We said there were 3 crystal structures we could use. So make sure you know those identifier codes of the crystal structures. They were 6KPC, 6PT0, and 6KPF. To download them, we would go to File, Get PDB. We'll type in the PDB ID one at a time. We're going to use 6K PC. That's our first structure. We can download our second. Oh, it's taking a little bit of time to. Okay. Get PDB. We'll just download 2. We'll randomly pick 6kpf. Okay, so we have those 2 crystal structures in our workspace, and we can view them. In order to move the protein around, if you just hold the scroll wheel on your mouse down and hold it pressed and move your mouse up and down, it'll move the protein. To view the entries in the table, click Table, and the 2 entries will pop up, and if we select, I have dual monitors, but I don't know how to screen share. I mean, I don't know how to in a recording show both my monitors, so I'll just do it in one. It's fine. Notice how if you select one entry, it'll go to that entry. If you select the other entry, it'll go. To put both entries in the workspace at once, hold down Control and then click the other one, and it'll display both, as so. Let's just look at one of the crystal structures for now. Oftentimes in biochemistry, we like to look at things in terms of alpha helices and beta sheets, which are part of protein structure. If you click Style and go to Ribbons, that'll display it as alpha helices. Cool. So this top part is actually the receptor that we're interested in. So from here down to here is part of the receptor that we're interested in docking something to. The stuff on the bottom is, I don't want to use the word fake, but it's an artificial region of protein that has been inserted by the scientist getting the structure to help it, to stabilize it, which will help get a crystal easier. So that's stuff we don't really have to look at or care much about, but the top part is the part of the receptor that we're curious about. CB2 is a GPCR. All GPCRs have 7 transmembrane helices, or 7 of these spaghetti corkscrew noodle type things, if you were to count all of them. The way to look at a GPCR is all GPCRs have this little tag in the back. I call it a tag. It's not really a tag, but that's just my word for it. They all have this little tag in the back. This one's in yellow. And if you look at any GPCR, they all have this. And this is always the back of the receptor. So if I spin this 180 degrees, I know I'm looking at the front of the receptor from front to back. Kind of like this. That would be the way to... I don't want to use the proper way to look at it, but the standardized way of looking at a GPCR. Because it's an agonist-bound crystal structure, there's going to be an agonist bound in the middle, which is this molecule in the middle. That's our agonist. And if you wanted to make the molecule in the center, our agonist, a little bit bigger, it's actually here in green. It's hard to see. If you click L for a ligand, it'll highlight it. And then if you click Style, you can display this as a van der Waals radii, which is quite large. You can see it easily. I prefer ball and stick model. And then if we click the L, we can zoom in on the active site of the receptor. And basically, it's called the active site of the receptor as, well, okay, so I'll put it this way. The orthosteric, the term for this binding site, where the normal endogenous ligands will bind for CB1 and CB2, it's 2-arachidonylglycerol and anandamide. These are the natural ligands that your body synthesizes in order to activate these receptors, and they all bind to this binding site, and the term for it is an orthosteric binding site. And then within the orthosteric binding site, you have amino acid residues that your drug will interact with. So for example, if I click this one, this is phenylalanine 91. This is tryptophan 194, and you could just kind of click around and look at different amino acids. This one is histidine. Cool. So when we select a crystal structure, I like to make sure that there is agreement among multiple crystal structures to show that the structure that I'm looking at is valid, I guess is a good way to put it. So what I like to do is take if there are 2, 3, 4 crystal structures all from the same receptor and all in an agonist or an antagonist bound state, I like to superimpose them to see if there is agreement among especially the amino acid residues in the binding site. We'll quickly do that. If I click my 6K PC structure, I can do the same thing, kind of to display it in a pretty way. Style, ribbons, all this extra junk at the bottom. I don't want to call it junk, but all this extra junk at the bottom is part of the G protein. This is a CB2 receptor crystallized in complex with the G protein. The G protein's the signaling molecule that allows for intracellular signaling of a GPCR within a cell. So you have like a receptor, and the G protein binds to it after it's activated. So here's my tag. Oh, there's my tag right there. So if I put it like this, that's looking at the receptor face on. And I could also click L to make my ligand a little bit bigger. Boom. Let's superimpose these structures. The best way to do a superimpose is to have one drug in the workspace, go to select all, and then go to edit, move atoms, and then display our other one in the workspace. And now notice how just one receptor moves, this top one. I'm going to put that tag in the back. It's a little hard to see now because it's small. Then I'm going to drag it kind of close to the other GPCR. Kind of like that. Press OK. And then now I'm going to zoom in. To superimpose structures, go to Tasks, go to Superposition, click Atom Pairs, select Pick, and then it says pick which atoms define the superposition. Basically, what I'm now going to do is select an approximately the same corresponding amino acid on 2 different receptors. So, for example, I'm going to if I select this one right here, that's threonine 34. I'm going to select this one right here, and those are in relatively the same position. So, see how there's this dotted line? That means when I click superimpose, it'll stack them. Same one here. Okay, and then I'll pick maybe a few more. Helix 2. And then I could probably just maybe even get away with that, to be honest. Maybe this one. And then notice how once I click the superimpose button, you get a pretty decent stack on top of each other. I could make this a lot better, which is what I'm going to do now. If I just, I'm going to delete all, and now I'm going to pick the amino acid residues that are just kind of stacked on top of each other. So for example, if I zoom in here, I'll select this one. This one's close. This one, this one. Let's go this one and this one. See how that does. It's a little better. We can always make it a little bit better by just going through this. So going through this process. Okay, see how it gets a little better. This is pretty good. We could actually kind of stop here and kind of look at what's going on. So now what we would do is click L. We go to the active site. And now what we should see is that the amino acid residues within the binding site show agreements in their relative three-dimensional position. So for example, if you zoom in here, you can see two tryptophans right here and right here. Right here and right here. Okay, and they're lined up pretty dang well. I'd say that's pretty good. And as for the other amino acids, I'd say these are in a pretty agreeable positions within the GPCR. I mean, you see there's like slight differences, but that's not really a big deal because there are other steps that we'll take in the future to alleviate some of that. So yeah, I mean, both these structures look pretty good, and we could use either of them. And I think that's where we'll stop today. Just kind of getting, oh, the other thing, very quickly, that AlphaFold structure, if you wanted to pull it inside your workspace, it's right here in my downloads. If I just click and drag, it'll download into Maestro. But we're not going to use the AlphaFold structure. AlphaFold's super cool. It's just, it's not what I want to do for this project. I hope you guys enjoyed that. I will for sure leave the free version of Maestro download link in the description of the video. I highly encourage you to download it. It's super cool. And it's a good way of viewing proteins, but you could also use, if you have Pimal or Chimera by Autodoc Vina, those work too. Oh, you also have to have a university email for the free version of Maestro to work. But with that being said, I hope you guys enjoyed this, and we'll keep going with this learning how to design drugs. Bye.